Hi, my name's Jim Murray, and this is a lab where I do a lot of my work. I think it's an interesting possibility that this could develop into some very important progress for mankind in general. So, as a result of that, I thought it would be a good idea to give a little overview of what I've been doing and what this is all for. I started working in alternative energy projects when I was 19 years old. I'm now 66, and I have spent a lot of time and a great deal of money coming to an understanding about things which most people do not choose to investigate. The result of those investigations is the type of equipment that you see all around you in this room. I'm going to be going over some of the aspects of those inventions and discoveries as we progress through this presentation. But basically, I think I should open by saying that my intention here is to demonstrate the possibility in the near future of having machinery with efficiencies that are absolutely unheard of. These things can be accomplished without violating any physical law, simply because of the fact that some of the things that have been discovered here indicate that not all of the losses which are the most parasitic in nature have actually been identified and included in the average engineering approach to the design of motors and generators. So with that, let me bring you over to the earlier section of the work I've done, and we'll progress from there. The machine that you just saw is called a Dynaflux alternator. I invented that many years ago in northern Michigan when I was working for Bethlehem Steel. And the story behind its evolution is pretty interesting, but we'll forego that to another time. More importantly, I think I'll concentrate on what the device actually does. In order to give you some insights into that, what I'm going to do is give you a really simple but effective demonstration about why electricity costs so much to produce. This is a samarium cobalt magnet. There's absolutely nothing unusual about it except for the fact that it's extremely powerful. If I drop this, it falls in the gravitational field just like any other object would. That's the whole purpose of showing you it separately, so you can see how fast it falls. This is a brass pipe. Now, when I drop this into the brass pipe, you might expect the same results, but believe me, it'll be very different, because it's going to take a great deal of time for that thing to transit the pipe. Now, the question is, why does that happen? See how long it takes as opposed to when I drop it in the open? The reason for that is that as this magnet moves through the pipe, its motion and its magnetic field create currents inside the material of this pipe. And those currents in turn produce a magnetic field of their own. And that magnetic field bucks the progress of the magnet, so that instead of accelerating at 32 feet per second, it just falls at a constant velocity. Well, the exact same thing happens in an electrical generator, except that the effects are a lot more expensive. Let me just get an armature for you to look at. This is a standard armature removed from the kind of generator that you might have being turned by a gasoline engine or a little diesel engine, something like that, so for auxiliary power in your home, for instance. You'll notice that there are coils embedded in the material here. And as this rotates through a magnetic field, there's a voltage produced in these windings. That's in concert with Lenz's law. But also, what happens is the minute you close the breaker and take current out of this device, forces appear which attempt to cause this to motor or to twist as a motor in a direction opposite to that which you are attempting to turn it. And so the prime mover, your gasoline motor or whatever it is you're running this with, then has to labor to overcome this back torque or this reverse torque in order to continue this thing turning at a sufficient speed to give you the voltage that you need to keep the current flowing. In very simplified terms, that actually is the reason why it takes so much power to turn a generator. Or, to put it in more succinct terms, the power in has to equal the power out. There isn't any advantage that you can seek which will increase the overall efficiency or reduce the amount of fuel that you're consuming. But that's only true of this particular geometry. Now I'll demonstrate a different approach. You noticed in the previous piece of equipment that I showed you, the shape was cylindrical. If you focus on this machine, you'll see that we're making use of a very unusual geometry in the rotor. It's actually an ellipse. It's an ellipse in 3D, but the cross-section of that ellipse is still circular or cylindrical, and so it can rotate between two field poles without any difficulty. Now there's a very specific reason for doing this. When we create a magnetic field with this winding, the flux comes down through here, attempts to cross over to the other side and return to the magnetic coil, and this is the only path that it can take to do that. So when this is rotating, the net result is that the flux in both of these pole pieces is actually oscillating back and forth. And when it oscillates back and forth, it's moving in a direction which is 90 degrees away from the direction that is used in a standard generator to produce a voltage. So it's actually shuffling back and forth horizontally in these pole pieces and creating a voltage in these windings. And then when we close the breaker and attempt to use that current, the result is that for part of the cycle it's going to be experiencing a resistance to motion, and for the other part of the cycle it's actually going to be experiencing an assistance to its turning. And as a result of that, we wind up with a totally different concept in generation and very different numbers to describe the efficiency of the system. It's a very long and laborious presentation to go through all of the numbers because it requires a thing called a segregated load analysis, which I think the audience would find very boring. However, you will be directed on this presentation to lectures and other locations on the internet where you can see lectures that I've already produced and interviews where I touch more deeply on these particulars. So if you have an interest in that, be sure to follow through and look at some of the other material that's going to be available to you. I think the best thing to do at this point is to give you a demonstration of how this actually functions, and it'll become self-evident as to how different it is from a standard generator. But before we do that, I think I'll just touch on what the equipment is that you're looking at. This is a DC motor, and it has on the back end of it a tach follower, which allows the motor to be to have a reference so it can turn at a fixed speed regardless of how the system changes. This is simply a drive belt that comes over here and runs a clutch assembly, and this clutch runs my generator, and the forward clutch runs a standard generator. And the reason for that setup is in case we want to make a comparison between a standard machine and the Dynaflux machine. Then over here we have the control console that runs all of that equipment, And in this upper chamber here is a what we call a DC drive, and that drive is what regulates the behavior of the motor. It's programmed to start the motor off at a slow pace and accelerate it at an even rate, simply because of the fact that to jerk this thing into the on position with none of this equipment being bolted down, you risk damaging something or breaking belts. So with that, I will start this thing up, and as it's accelerating, I'll tell you a little bit about the instruments that are on this panel. The top meter here is your input voltage, this is your input current, and this is the shaft speed. The two center meters monitor the magnetic field. This is going to be the generator field voltage, generator field current. This is the output voltage, the output current, and the output frequency of the generator. You can see it's already building towards 60 cycles. So when this speed reaches 1800 RPM, then we'll be ready to bring up the magnetic field. There it is now, it's about 1800. So I bring up the magnetic field. And now we're actually generating the voltage. You can see there's 24 volts coming out of that machine. And when I turn this breaker on, the two floodlights over there will assume the electrical load. So those lamps are now being powered directly by the energy that is made available by the rotation of that machine. And if we had run the other machine first, we'd be able to contrast the behavior between a standard generator and this machine, and you'd see that this hardly presents a load of any sort whatsoever to the prime mover. So I don't want to get into too much detail because, for two reasons, these lectures can go on indefinitely. There's really a lot to transmit to other people, considering I've been working at this for more than 45 years. So rather than bore you to death, I think it's more interesting to keep the thing somewhat superficial at this point and move from one machine to another and explain the benefits and the progress that the research has enjoyed. So with that, we'll move to another device. Okay, this is a machine that we call the transforming generator, and the reason for that is because this machine actually incorporates two separate technologies in one embodiment. It's both a generator and a transformer. And in order to demonstrate that and then explain why it's useful, I'm going to run this device for you and produce an interesting little experiment here. The main reason I built it was actually to study the difference between EMF and voltage. Now I know that most people think that they're the same, but they're not. An EMF is called electromotive force. That's the force that pushes current. And the current passing through an impedance, which could be a resistor or capacitor or inductor or whatever, actually the pressure of the charge that cannot flow through the impedance simultaneously is what develops the phenomenon that we call voltage. So it's okay to use them interchangeably for certain calculations when you understand what you're doing, like in the application of Kirchhoff's laws for studying mesh and node equations, but there are times when you really have to keep them segregated, and so I built this particular machine to allow me to concentrate on the force aspect of this separately from the voltage aspect. Now, a lot of the results of that are proprietary. I'm not going to go into the details, but I will show you a couple of interesting features, and we'll use that to further the explanation of the machine. First of all, there are two sets of windings in this machine. One set is brought out on this pair of lines, and the other set is brought out on this pair of wires. Now, these two conductors go directly to this 300-watt bulb. The ones from this side do not come directly to this bulb. They go through this little selector switch, this little knife switch that's down here. One side of that knife switch has a copper bar across it, which essentially constitutes a short circuit. The other side will allow the connection to be made to this bulb. It's important to understand that ahead of time so that you can grasp the significance of the demonstration. So with that, I'm going to bring this guy up to speed. I'll be using a RPM meter to set the high end of the RPM so that we don't blow any fuses. Okay, we're at about 2200 RPM, and that's going to be sufficient to demonstrate what I have to show you. So the next thing we're going to do is turn up the field on the generator so that it starts producing a voltage. You'll notice a glow will appear in that lamp over there when we reach a certain setting. There it's starting to glow now. I'm going to take this meter and we're going to do a couple of voltage measurements just so I can make a point. First, I'm going to turn the lamp off. So now there's no load on that particular winding. We have 59.2 volts, almost 60 volts. Now if I turn this lamp back on, when we get the glow again, now that we have the glow, we'll take a voltage measurement and you'll see that we only have 15.7 volts actually appearing across that lamp. 15.6, okay? So most people would say, well, we just had 60 volts there, where did the other 45 go? It's actually sitting inside the generator across the windings in a phenomenon known as inductive reactance. It's actually consuming that other amount of voltage so that it cannot reach the lamp. Now, normally in a standard generator, the way they get around that is they have a whole series of windings and they connect them all together. This machine only has 2 windings, and I'm going to be able to put the full production voltage into that lamp just by making a slight change in the circuitry. You notice all the controls are underneath. I'm not going to touch a thing under there. So the setting on the field is going to remain absolutely the same. But I am going to close this little switch, as I mentioned to you before, and we're going to go first to the short circuit, which is a copper bar that's placed across the output of this switch. That's going to cause a current to flow in this winding, which will change the magnetic coupling coefficients between this coil and that coil, and it's going to release the full potential of that coil into the lamp. See that? Now the interesting thing is that this side of the coil to that side appears as a capacitor, and that's the reason it can do that. It actually resonates that winding, which means it gets rid of all of its resistance to the total amount of flow of electricity. But if I put this to this side, you notice now both lamps come on, and that's because this side opens that side of the generator, and this side opens this side of the generator, allowing the total amount of power that's being created to flow into the lamps. Now, there's some very special reasons for investigating this kind of thing, most of which have to do with the way I've designed a lot of the equipment in this room. But I wanted to demonstrate that in particular because it's a very fundamental concept, and it will appear in every single machine that you're going to see throughout the course of this demonstration. So this little mechanism here is referred to as the SERPS unit, which stands for Switched Energy Resonant Power Supply. And basically this makes use of a principle of power reflection that Tesla worked on 120 years ago. And it actually forms the basis of at least part of each of the machines in this room, whether they're totally electromagnetic or whether they have electronic controllers associated with them. So the basics of this, just bear in mind, will be reappearing in most of the other equipment that we show. Here we have two Yokogawa watt analyzers. The top one here is dedicated to monitoring this resistor, and the bottom one, which is a much fuller, more complex device, is going to be monitoring the power coming out of this transformer. And basically what this equipment does, there are some special switches on here which switch the circuit configuration at certain ideal moments, and that's all done under the guidance of an embedded processor which resides in this little case here. And it's programmed to make those switches in such a way that we encourage two things to happen. On the first portion of the cycle, we're actually going to be taking power from the power source or from the power line, and that's going to come through these switches, and it's going to go through this resistor. In the second half of the cycle, the power is literally going to be sent back to where it came from. And it's still going to pass through this resistor a second time. So the resistor will get hot, which is what it's supposed to do. This meter will show you how much wattage is actually being dissipated in the resistor. The total wattage, regardless of whether the current is coming or going, so to speak, in this resistor is going to constitute what we call the absolute power, because it's going to produce a heating effect irregardless of which way the power is moving. But that's not the case with the power coming from the source, because when I draw power from the source, that constitutes positive wattage. And when I return power to the source, that constitutes negative wattage. So this device is actually going to be monitoring the differential power, or the net power, if you prefer. And that's the reason why you're going to see a difference between these two readings, even though the power is going into the same device. Now, a lot of people would conclude that you're creating energy. It's nonsense. You can't create energy, and I wouldn't waste my time trying. But you can manipulate power in such a way as to access its full capability, and that's what all of this equipment does. When you see this thing in operation, you realize that the very first machine I showed you over in the back, the Dynaflux alternator, is actually doing the same thing, except it's doing it electromechanically. It doesn't have to be electronic, but the principles are the same. So with that, let me go through some preliminaries. This is going to be the voltage reading on the top. The second one is going to be the amperage, and the bottom one is going to be the wattage. Down here, it's going to display volts, amps, and watts, but I have the option of looking at other parameters, and I will do that once we get this device turned on. So with that preliminary information, I'll switch on the processor, and hopefully we'll get some interesting numbers. So now you can see that we are pulling or dissipating in that resistance 28.92 or 91 watts. But the actual reading that the line sees is only 8.77 watts. Okay? And that's not because we're creating any power. It's because of the fact that when you return power, you get a different effect, because this is reading the net power consumption, not the absolute power consumption. Now you might say, well, is there any proof of that? Yes, there is. If we switch to VARs, you'll notice that even though we're running a totally resistive load, I have 222 VARs, which is totally reactive power. Okay, and that's the reason that you have a VAR reading. The VAR reading up here would be 0. Now if we move to power factor, the power factor is only 0.039, which is also indicative of a highly reactive load. Now you might say, well, where's the reactive part of it? The reactive part of it comes into play because of the fact that when you return power from whence it came, as long as you are doing it in a rhythmic fashion, you're actually creating a VAR. Even though it can be in phase with the voltage, which is the case here, otherwise we wouldn't be looking at watts, you still are creating VARs. And so just to give you an example of where we're at with this from a standpoint of efficiency, if we take 30.31 and we divide that by 8.68, and then we multiply that by 100, we wind up with 349.19%, which is a little bit unusual. And yet, it's relatively simple to do. It actually can be done, and the only reason why this particular circuit wouldn't be applicable to general households is because of the fact that that low power factor would be a reason for the power company to penalize you, and they would charge you just as much or more for having a low power factor, irregardless of the fact that it would be saving them money. They don't want it to save you money. So the point here is that by using this type of technology internally, we can secure higher efficiencies on other devices that will allow you to enjoy a reduced utility bill without aggravating, might be a good word, the local power companies. So with that, we will now move over and do a demo that actually shows this feature in operation. So what you see here are some of the latest developments in the Dynaflux department, which all transcend from the original device that I showed you, the Dynaflux alternator. Now, these machines are motors as opposed to being alternators or generators, and I'm going to demonstrate them for you along with some interesting little behavioral characteristics. But I wanted to start off by showing a rotor that's typical of what's inside these machines. This is an elliptical rotor. As you can see, it's not round. It's an oval or an ellipse. And you might say, well, how can that turn in a machine? Well, very easily. When you have this tilted at 45 degrees with respect to the shaft, it just spins away without any difficulty. The thing that's interesting is it does display that wobbling motion like we saw in the first machine, and so these devices have to be counterweighted in order to suppress the resulting vibration. But other than that, this is what makes them go. Now, this first machine is a DC Dynaflux motor, and the electronics that are running it, both this little computer and the switching electronics that are on this disc here, are far too small to bring that thing up to full power, because this was an experimental circuit that we used to basically establish the ground rules for this type of circuitry. And unfortunately, after we figured out exactly how to build it, we didn't have any money to upgrade it. But we will still demonstrate exactly how it can work and the benefits of using this approach. Now, there's a couple of things that are important to point out. First of all, this is a computer here which is very similar in the way it functions in concert with these switches to the previous demonstration I showed you on the SERPS machine. This is the motor itself, and this device here is the shaft position indicator, which, as you can see, is wired directly to the computer, and it sends signals to the computer telling the computer where the shaft is in space, and as a result of that, the computer can then make use of certain algorithms and decide when the best moment for switching and reversing the power flow. Now, in this case, since we're not attached to the line with the motor, the power that's going to be reversing its direction is the power that's coming from the feed and going into the coils or coming back out of the coils. And this device here is what monitors that and controls that. So there's two modes of operation here. One would be to just run the motor directly, in which case the recaptured power, which is trying to oscillate back toward the source, is going to be directed into this big lamp. And so it has to be used up with this type of a system, or else you're going to have a problem blowing up your power supply, which we certainly don't want. So initially, when this thing revs up, you will see this lamp come on. Now what I'm going to do at a certain point is literally turn that lamp off, and when we do, you will actually be able to see the effect of what happens when that power, instead of going to this lamp, is actually sent back to the source. And that will be monitored on these 3 watt meters. This first watt meter is the actual power going into the motor itself. This is the recovered power, which is going to be coming out of that light bulb. And this is the actual power drawn from this power supply. So I'm going to have the cameraman focus on this during the course of this demonstration so that you can see the effect of making this transition from using the recovered power just to light the light, as opposed to sending it back to the source for reuse. So with that, I'll start up the motor. Now, you can see that there's a small leakage voltage already appearing on this voltmeter here. That's simply because of the fact that this variac doesn't go completely off. But this other voltmeter, which is connected across the recovery channel, is showing 0. So what we're going to do is bring this power up to the point where we've got about 30 or 40 volts. And then I'm going to give the motor a little kick, because this is not a self-starting machine. And as she starts to turn, you can already see it's recapturing power. The power that's lighting that lamp has already been used to turn the motor. So we'll bring this up to about 100 volts on the recovery side. And then we'll take a look at some of the readings on the watt meter here. Okay, so you'll notice that this watt meter is a little above 150 watts. We're reading the bottom scale. The recovered power is about 95 watts, which is winding up in the lamp. And this wattage is 150 watts being applied to the motor. Okay? Now what we're going to do is deliberately switch off the lamp. And when we switch off the lamp, you'll hear a little noise, which is the DC to DC converter actually taking the power that was going into this lamp, converting it to a different DC potential and sending it back to the power supply. Now, since we're going to be using this power over again, you want to watch what happens to this first meter when we shut off the lamp. Let me know when you're ready. So now the power that we're taking from the wall has dropped down to about 85 watts. There's no recovered power because we're not dissipating it in the lamp. And the power that's going to the motor is actually 5 watts higher, so it's 155 watts. Okay, so we're literally feeding power back to where it came from, which is the reason this dropped down to the lower figure. And we're only taking enough power from the wall to cover the losses that are incurred in operating this equipment. So here again, we can look at an anomalous feature of this device. If we take 150 watts, we don't have to have 155 to make the point. 150 watts divided by 85 watts times 100. That's 176.47% efficiency. Now that's system efficiency. It is not conversion efficiency. The motor itself is well within standard 70 to 75% efficiency area because it was never engineered to perfection. But just imagine if this was perfectly engineered and all of this circuitry was brought up to snuff so that this could be run at its maximum design criteria, you would actually see even better numbers than we're showing right now. So this is what you can do with applying energy resonance and Dynaflux characteristics to a DC machine. And I'm going to show you some even more interesting effects when we move to an AC version of this. But first I'm going to turn the lamp back on and return the system to its previous mode of operation. Now you see right away we got the wattage returns to the value that we were looking at before. The input and the output are approximately the same, and the wattage that's dissipated in the lamp is registering as before. Okay, the equipment that we just showed you in the film is actually a AC version of the Dynaflux principle. The small machine here is the one I'm going to demonstrate next. And the purpose of this demonstration will be to highlight the fact that it is possible to have rotary motion with a three-phase field and produce very, very small amounts of back EMF. Once I've made the illustration evident with this device, I'll then do the same thing with a much larger motor, but I won't be able to grab the shaft on that motor because I'm very attached to my hands. So I'm going to focus primarily on the small motor for the more rudimentary demonstrations. Now this motor does not have internal balancing, so there will be a limit to how fast I can make it spin and keep it on the table here. But let me bring it up to speed. Right away you can see the amperage building. It's already pulling 5.77 or so amps. Now the interesting thing is it'll pull that same amount of amperage whether it's running at high speed, low speed, or no speed. So I'm going to grab the shaft, and as I slow the motor down, you'll be able to see that because there's no back EMF in this motor, or very, very, very little, that when I slow this down, there'll be a very, very small change in the current, even to the point where I can seize the shaft. So now the shaft is seized, and we've got 6 amps flowing. If I let it accelerate, you can see that it's going to be just a couple of tenths of an amp difference. Now it's turning up to full speed, and we only have 5.6 amps. So basically 0.4 amps is the difference that you notice in the current as a result of the small amount of back EMF that's involved in this motor's operation. Now what I'm going to do is transfer the power from this motor to the large motor, and I'll give another series of demonstrations there. But that motor is going to be demonstrating a feature called compound resonance, where I actually cause a beat to appear between the line frequency and the angular frequency of the rotor. And so in order to do all of that, we have to have a capacitor bank which also changes the power associated with the movement of that shaft. This motor has no capacitors involved, so it's very easy for me to just reach over and stop the shaft. I wouldn't recommend trying it on the large machine. So here we are with the larger Dynaflux machine. This is a 3-phase Dynaflux AC motor, and as you can see there are different capacitor banks associated with its operation. For this demonstration I'm going to be using the low power stuff, which constitutes the 3 gray capacitors that you see in the background. These are for much higher voltage operation, and they're not connected right now. But there are essentially 3 tank circuits used in this machine's design, and those create a resonance phenomenon that interacts with the angular resonance of the machine to produce the net result. Now, as I bring the speed up on this thing, you'll see that the amperage goes up accordingly, just like it did on the small motor. The difference is that if I didn't have those capacitors on there, it would take about 1500 volts to run this motor with the type of internal reactance that it has. But we're going to be doing it around 100 volts. So that's one thing to bear in mind. And the other thing to bear in mind is that this thing has some really unusual load characteristics. I'm not going to be able to show any of that because we need the pony brake or the dynamometer, and I need a whole host of equipment that's not set up for this. But just to give you a taste of it, this is a synchronous motor, and one of the more unusual aspects of it is that it's self-starting. So in a lot of synchronous machines you're going to need an auxiliary device to start it with, either a mortise or winding or something of that sort. I can just do this by bringing up the voltage. So that's what we'll do first. This motor is a little on the loud side considering its size, so we're probably going to have to shout a little bit to get some points across, but I think the majority of the information will be self-evident. So with that, I'm going to start the machine up. and you can already see she's pulling about an amp now. There she goes, she's starting to rotate. 1.9 amps. And you notice that as I apply additional voltage, the machine accelerates, which is not typical of a normal synchronous motor. But anyway, when we get up to about 6 amps, you'll be able to hear a difference in the tone of the motor. You'll hear that beat frequency, if I can let you listen to it. And then all of a sudden it'll switch into full resonance, and you'll see the current jump about 2 octaves in the process. There it is, wide open. I certainly wouldn't attempt to grab that shaft under those conditions. So it jumps from about 6 amps to 18 amps, and the voltage is about 100 volts. And if we took those caps off the line there, it would take about 1500 volts to run this motor. Now this motor is not yet fully engineered. It's got some problems, but it's very, very worthwhile in terms of its applications and the type of efficiency that it's capable of delivering. Right now, the biggest problem we have besides money is the fact that these laminations are not adequate for the way in which we're using the magnetic circuits. And we're going to have to invent our own solution to squelch the eddy currents that are involved. But I've done a lot of experiments with different materials and different arrangements for the salient pole projections. And I believe that the solution is very doable. It's just a question of the fact that we need a good team to concentrate on this and a financial wherewithal to support them. So this last machine is also a DC motor. It's a very different one from the others I've shown you. It's a reluctance motor with a rotating field, and the field is produced by an external switching device, or circuit controller, as we call it. This circuit controller is electromechanical. It's actually motor driven. But ultimately, if we can get the funding, I will replace this by a totally electronic device, which then incorporates the recapture features and all of the normal things that you would have a computer do to optimize a motor. And that will allow us to get unheard of efficiencies out of this device. But in its present state, what I can demonstrate, which is pretty interesting, is the fact that you actually can produce a constant torque over a fairly large speed range. What's going to happen if we go too fast with this thing is that it does get out of sync with the controller, in which case the motor loses its orientation. But anywhere from about 0 RPM up to almost 500 RPM, this thing is very predictable and very linear. Our studies have demonstrated that with the proper electronic controller and the necessary embedded processors, we could probably take this up to 10,000 RPM and still demonstrate the same characteristics. So with that, let me switch on the power and give you a quick demonstration. Now, one of the things you'll notice when I turn on the power is that this rotor will jump to its null position, which is going to be an exact imitation of the position of the controller. And these two things always turn in synchronism under normal conditions. So let me get this turned on. And there she turned. Now, believe it or not, we have full torque right now on this motor. I mean, if we had the equipment hooked up, I could demonstrate that to you with meters, but I just measured it the other day for some folks that were here, and it's 54 inch-pounds of torque. So that's a pretty impressive number. And we're only pulling 2.28 amps on both our power windings. So that's a pretty significant amount of torque considering the investment of current. Now, as I turn up the speed, you'll notice that these two guys turn together in synchronism, and the torque is just as frisky as it was before. I can't stop it, and this shaft here is about 2 inches in diameter. Actually, if we applied a pony brake to the larger diameter of the pulley, you probably could seize it, but it would be it'd still be difficult to do. Well, I'm accelerating it manually. We still have that same frisky torque with no real problems. And if I lower the speed, it stays in sync with the transmitter or the controller. Well, this, out of all the machines that we've showed you today, this is probably the one which is closest to commercialization. What we need right now is enough funding to finish the design of the electronic controller and probably build another prototype as well. But anyway, that's what's on the agenda, and these are the types of things I've invested most of my life in perfecting. The other equipment that you see in this room represent other technologies, which are just as interesting, but they're a little bit more obtuse than what I've showed you so far, and so I'm going to limit my presentation to the electromagnetic stuff for now. I thank you for your time and attention. Don't forget that you can get to the lectures and the interviews that are on the web by going to the links at the bottom of the page. Thank you for your attention.